combinational logic, where we talk about what kind of combinational logic we would be interested to look at. For example, ratioed logic. So long back. So see, one challenge with static CMOS is that for n number of inputs, you have 2n number of devices. And of those 2n devices also, the PMOS, that is the half of those 2n devices, n devices are also larger. Are you able to see this? In a NAND gate, 2-input NAND gate, how many devices do we have? 2-input NAND gate, how many devices do we have? Four devices. In a NOR gate, how many do we have? 2-input NOR gate?
4 only, sir.
Again 4. So at least 2n devices are there in static CMOS. And what about the size of NMOS and PMOS there? So in the NOR gate, the PMOS size is 4 times that of the NMOS size. In a NAND gate, it is equivalent to an NMOS size in a 2-input NAND gate. So what do? Now we want to look for, is there a way to reduce the total number of devices? Why do we want to reduce the total number of devices? What's the importance of reducing number of devices?
Area reduction.
Yes. And in VLSI, area is?
Gold.
Gold. We want to save gold. So we want to reduce area, come whatever may. So now we will look at a few methods, a few techniques to reduce area. By, for example, in this particular slide, you will see completely doing away with the pull-up network, for example. So what do? Instead of all those PMOSes, I will just put one resistive load. What's the problem with one resistive load?
Control loss, sir. We can't charge our output whenever we want. Exactly. It will be always charging.
Leakage. Fabrication is difficult.
Okay. So when you say that instead of static CMOS, I will put any other load, whether it is resistive load or depletion load or PMOS load, since that load is always on. What happens? We will observe leakage. We will observe continuous static current from VDD to VSS. And different types of designs were proposed. Resistive loads. So in technologies when PMOSs were not available, then resistive loads or depletion loads were the only options to be used. Once the PMOSs started to become available, then PMOS loads were used. But these PMOS loads were always on. Now, we just saw that by using these always on loads or resistances and depletion loads, what is the challenge that we expect? That the output will not go to pure zero. Cannot, because PMOS is always on. Some current will come either from RL or the PMOS or the depletion load that we have put. Are you with me on this? Any questions still here? Hello? You can put a +1 or something in the chat window if you don't want to unmute and speak. No? I will not move forward until I get a feedback.
Sir, okay. One thing, sir, if the load is big enough, then we can obtain kind of a clear zero.
Yes. So what will be the challenge then if the load is, suppose this resistive load is very resistive? Then I will get an almost good zero. But what is the challenge?
Sir, current will be low.
Charging would be.
Current will be less.
Yes.
So when I have to take F to 1, that will be very slow. Are you able to see this? The charging will be very slow then. So you cannot really keep the resistance to be extremely high also. And moreover, if you want to keep this resistance to be very high, if you have a real resistance there, then that resistance will take a lot of area. If you have a PMOS there or a depletion load there, okay, area may not be that much impacted, but you will have, in all the three cases, whether it is resistance or transistors, you will have much larger rise times. So one thing we already discussed, that the noise margin would degrade. The low voltage will not be zero. Low voltage will be in the ratio of resistance of the P network upon resistance of the resistance of the pull down network upon resistance of the pull down network plus RL. And the propagation delay will also, in the case of rising, be dependent on RL. So if you make very large resistance, then the rise time will be very, very large. So this is not really a good way to design, but you see, we save lots of area. So we may want to design it somewhere. So these are the active loads where we have, in this case, a NMOS only technology, and in this case, a PMOS load. So in our technologies, we always have PMOS, so we may want to do it like this. But we see that there are obvious challenges. If, for example, I have a pseudo NMOS design where they have a PMOS load, because it is small and everything, I have a PMOS load, then what happens? Then when just one of these inputs is on, the other three are off, at that point of time, the current that is sunk from here will be, or the ratio of current sunk from here, or the resistance of the PMOS stack, and the ratio of the NMOS stack, resistance of the NMOS stack, will be such that my VOL will be different. So you will see that as my more and more transistors in that NOR gate turn on, I will get a I will get a better zero.
So
Are you able to see this?
Not exactly, sir. I mean, why VOA is changing here?
Okay. So let us say the PMOS resistance is 10K. And NMOS resistance is also 10K. Let us say 10K nahi kahenge. Let us say NMOS resistance is 2K. Each of these NMOSs has resistance 2K. So when all four of my NMOSs are on, what is the effective NMOS resistance?
2 by 4.
500 ohms. 500 ohms.
So what is the value of VOL? Approximately?
So the voltage at the load basically.
1/5 of VDD.
1/5 of VDD by 500 by 10,500, no?
Okay, yes.
Approximately VDD by 19. VDD by 21. So almost even within 5% of VDD. Okay. Now let us say only one of them is on. Then what is happening? Are you able to see this?
Yes.
Hello.
But why won't we, for example, if we know that we are using a pseudo NMOS, then we can design a PMOS also to be that equivalent resistance like happens for the
कितना बनाओगे? चलो, tell me ना. Tell me a value. How much would you want the PMOS resistance to be? See,
like,
finally, ideally, you would want equal resistance on PMOS and NMOS so that you have almost equal delays for rise and fall.
yes, sir.
So मैंने तो अभी बहुत खराब बनाया. I made it 10K. Whereas NMOSs are 2K. So my rise time will be 5 times more than fall time already. You propose what number would you want to use? Let us use that. I have no problem. Let us find out with that number. Tell me.
So if we use 2K for the PMOS,
PMOS?
also. Yes, sir.
Let us use 2K for the PMOS. Then what happens when all the four outputs are 1?
Okay. And it will be
Same 500.
So output will be then at VDD by 4.
yeah, yes, sir. Okay.
Now let us say when 1 is only 1.
Then it will be
That will not work for you.
Okay.
Are you able to see this?
Yes, sir.
Hmm? So when we do, so what this also means is that when we do ratio logic design, pseudo NMOS, pseudo PMOS, the way we size the NMOS and PMOS has a very significant impact on VOL and all those things. And that is what is shown in this slide. That as you size your PMOS up, what happens? You reduce the PMOS resistance, but my VOL reduced. My fall time increased significantly. Are you able to see this? This is exactly the same discussion you were having just now.
Yes.
So, not very interesting, very complex, in the sense that if while we save area, we save a lot of area actually. All the PMOSs are gone. So in that NOR gate, imagine the PMOSs would have, if the NMOS is sized 1, the PMOS would have been sized, it's a 4 input thing. What would have been the size of the PMOSs? Hello?
4 times the size of
4 times.
8 times.
16 times. It's a
16,
4
sir,
input.
16. 16,
It's a
sir.
4 input thing.
Yeah, 16, sir.
So 16 into 4, you've saved how much? 64 units out of total 68 units.
Yeah.
Huge area saving, but much, much more complex, much less noise immune. So what do? We say, okay, and much less noise immune. Additionally, the rise time and fall times are very, very skewed and everything. So then the idea was, okay, let us do one thing where we say that during an active cycle, I will have an additional PMOS which would turn on. So what does this PMOS do? During the rise time, it would take it up fast. But when the system is falling, so initially it will fall to only say, let us say VDD by 4. But then once this PMOS goes off, enable goes high again, then this would fall to 0. Almost 0, because this is very resistive. We can do that. Hello?
Sir, I
Can
didn't
you
understand
repeat?
this
Can you
part.
repeat this, sir?
Sorry?
Can you repeat this part?
Yeah. So what do you want? In the earlier case, we saw that first, if I keep the PMOS to be very resistive, my rise time would be very bad. Okay, the 16% and 5% is fine. I'm not worried. So to get a good rise time, what do I want? I wanted the PMOS to be 2K. But with 2K, this was the kind of values I was getting on my output. Unacceptable. So what to do? So the idea is that in parallel to this 10K resistance, put another resistance, put another PMOS, which is slightly larger, so that effective PMOS resistance is now 2K. Okay. Now, when the evaluation is on, so this PMOS will be on only during the evaluation period. When the evaluation is on, my effective PMOS resistance is only 2K, so the rise will also be fast. But once the evaluation closes, I would come to this 10K wala scenario. And then my output would be at 5% VDD and 16% VDD. So I get the best of both worlds. Are you able to see this now?
So, but we would have to add some logic for enable signal also.
Yes, but that you can, my circuit is to be evaluated. I'm now evaluating my combinational circuit. So at a global level, you can add one signal.
Okay.
At a global level, you add one signal, but overall you save.
So at the VOL, at the output, I want the exact VDD pair. So this 16 and 5% I shouldn't get now. I mean, I should get the exact VDD.
No, but VDD you will get.
Yeah, but I'm getting this variation like 5% and 16%.
Yeah, that is dependent on inputs. That is the challenge with ratioed logic. But even 16% of VDD, which means it will still be considered as 0. much lower than VDD by 2.
Okay.
Much lower than VDD by 2. The other case is where the problem is.
Sir, what do you mean by evaluation phase exactly, sir?
Now, what do you think I mean?
Sir, should it be when should my NMOS be at higher logic? When do we when do we want our output to change? I don't know, sir.
Imagine, logical है. I'm not used a term which you do not know. In English, you know, na? English meaning क्या होगा evaluation का?
Whenever we want our output to be 0 or 1, according to the circuit definition.
I want my output to be 0 and 1 at all times, Vaishnav. Because otherwise there will be large amounts of currents flowing.
Yes, sir.
So something else. What else could be enabled for? What else would this evaluation mean? Anyone else who can help Vaishnav there? What do you think evaluation would mean?
The charging and discharging phase, maybe?
Hmm?
The transition time of the charging and the discharging when it's happening.
Okay, that is the evaluation. That is the time when your gate is getting transitions at inputs and you want to evaluate what is the output.
Yes, I think so.
So in a synchronous system, when the clock comes, that is when most of the gates toggle. That is when most of the inputs will toggle, because the flip-flop will give outputs only at that time. Otherwise, flip-flops will also have their output stable, is it not?
Yes, sir.
Yes, sir.
So you can say after the clock comes, I will have a 20 or 200 picosecond enable pulse, so that all the combinational gates in my system would evaluate. Can it be done?
Yes, sir.
So that is what we mean.
Yes, understood. Thank you.
So adaptive load means that during the evaluation phase, you have additional PMOS which is turned on, so that wherever signals have to rise, they can rise quickly. Because the output of this signal S, this gate S, has to go elsewhere also, is it not? So there is a path. We're just not designing one gate, we are designing a path. So wherever this goes, then it will do its own action there. Yes, Deepank?
So I have a doubt that we are switching the enable PMOS, right? And we are saying that it has to be much larger than M2. But I thought that since M2 is the one which is always on, and during the falling phase, to save the leakage, M2 should be larger since M1 will be off then.
During the static phase, when nothing is working.
No, when we need the low output.
So you do not know what the inputs are now, because if you do not know the inputs, how can you tell the outputs? You can only tell whether it is an evaluation phase or not.
No, sir. My doubt is, suppose one of the input is high.
No,
and
Deepank. Step back. This is a NOR gate, 4-input NOR gate. If you have to make the control of this PMOS based on the inputs itself, then you are actually going for a static CMOS implementation, aren't you?
Right.
You will have to put a gate to generate enable signal now.
Okay.
The entire effort is to save area.
Right.
But
then
you want to save area, so enable is to be generated irrespective of any input change.
Okay.
Clock comes, you generate input. You generate enables because you know now evaluations have to happen.
So we just need to save the rise delay in this case and saving area also.
Yeah.
Not leakage. Leakage is not the focus here.
No, leakage is saved because in the static case now only M2 is on. See, why would you not have made M2 much larger?
Okay.
Had you made M2 much larger, static power would have increased significantly.
Right, sir.
Now you've actually saved leakage by this method without compromising on rise time. You've done both
Okay.
now.
Right, sir. Right. Got it. Got it.
Okay.
Thank you.
Is this point clear to everyone?
So, sir, in effect, we are trying to basically, with this effort, we are trying to make the delays again same, like the rise delay equal to the fall delay. This is what we are
Yes.
trying to do.
Yes. That is what our attempt is.
Okay.
That is what our attempt is, that rise time and rise delay and fall delay should be almost equal, because if they are not, then at a system level, you have to put in a huge penalty in terms of managing setups and holds.
Yes, sir. So because earlier the fall was already less, so we had to make.
Yes.
Okay, sir.
Okay. So this is the adaptive load. Then this is very interesting. This is same kind of circuit, but instead of putting this PMOS to be always on, you are making a differential output logic. You're making a differential output logic where you say that instead of PMOS being controlled statically by a at 0 or something, and then me putting two PMOSs in parallel, adaptive load, whatever, if I anyway need both the polarities of an input, of an output, if I already need both the polarities of an output, then let me use this DC VSL logic, where what happens? We actually get full 0, and we actually get full ones and also full zeros. Because why? Suppose out bar has to go to 1. When out bar has to go to 1, what happens? This PMOS will turn off. So out will go to a clean 0. Out going to clean 0 means this PMOS is fully on. And this 1 will be strengthened. So noise immunity is also recovered, and you also save area. You can have these M1 and M2 large enough so that delays for rising and falling are similar. Are you able to see this?